In this lesson, we're going to go over combining probabilities. Specifically, we'll learn to calculate the probability of and events of dependence, calculate the probability of or events, and then calculate the probability of at least one event occurring. So to get started, and probability deals with independent events. Two events are independent if the outcome of one does not affect the probability or the outcome of the other. So for instance, when you're rolling a dice and you're rolling it twice, the probability of the first roll is independent of the second roll, or vice versa. Whatever is rolled the second time doesn't depend on what's rolled the first time. So if two independent events A and B are individual probabilities, let's say P of A and P of B, then the probability that both will occur, you multiply the two. So probability of A and B is equal to the probability of the first event times the probability of the second event. And so this can be extended to different independent events. Okay, so here we go. Example, rolling 3 dice. What is the probability of rolling 3 sixes in a row on a single die? So the way this would be set up, you have to determine what type of event it is in order to know how to calculate the probability. So when you're rolling a fair die, the first roll or the second roll doesn't depend on the first roll. The third roll doesn't depend on the first or the second rolls. So these are independent events, and so we would calculate the probability of each event and multiply. So what this looks like, and so for these problems, I'm going to draw it out on the screen, and then the following slide will also show the mathematics typed out. Okay, so on roll 1, the probability of rolling a 6 is 1 out of 6. Okay, there's 6 possible options. We want one of those. We want the 6. Roll 2 would be 1 out of 6, and roll 3 would be 1 out of 6. So in order to count the probability of a 6 and a 6 and a 6, would be 1/6 times 1/6 times 1/6. When you're multiplying fractions, you multiply the numerator, so 1 times 1 times 1 over the denominator. Okay, so you multiply straight across the numerator, 1 times 1 times 1, and straight across the denominator. So this becomes 1 out of 216. Okay. The software might have you enter a reduced fraction or a decimal. Okay. And so on the next screen, again, probability of 3 sixes in a row, 1/6 times 1/6 times 1/6. Let's talk about dependent events, another and type of probability. So two events are dependent if the outcome of one affects the probability of the other event. So picture like a bag of candy, almost at Halloween. So a bag of candy, and you want to know the probability of drawing a certain candy after 3 tries. Well, the amount of candy left in the bag after the first try is going to affect the probability of the second try. So this has to deal with when you're taking something out. So with the candy example, if you take out a piece of candy on the first try, for instance, there's less candy in the bag now. So that's what makes it a dependent event, because the outcome of one depends on what happened. So the probability that dependent events can occur together is probability of A and B, is equal to probability of A, probability of B given A, which we'll talk about in the example. B given A has to do with the event of B happening given that A has happened. So you assume whatever you wanted first has happened, and then you calculate the probability of B given A. The important thing here is that the denominator changes with the possible outcomes. So for instance, with the candy example, after I've taken one piece of candy out, there's now one less piece of candy in the bag, which would change the denominator or the possible outcomes. So jury selection. So a 3-person jury must be selected at random from a pool that has 6 men and 6 women. What is the probability of selecting an all-male jury? Okay, so for this one, so our probability of our first person being a man is, I'm just going to call it man 1, would be 6 out of 12. So there's 12 total. There's 12 possible outcomes. We'd be happy with any 6 of those being male. So now the probability of the second one being a male. So this has to do with probability of, let me erase this and use the language, probability of male 2 given male 1. Okay, so now, assuming that the first pick was male, there's now 5 males to choose from because one has been selected, and there's one less person in the pool. So the second of Probability of the second person being a male, given that the first was a male, is 5 out of 11. And then probability of person 3 being a male, given M1 and M2. So considering the first two before it, assuming that person 1 and person 2 were male, now there's only 4 male left in the pool and 1 less person. So 4 out of 10. So what this looks like is probability of 3 men would be 6 out of 12 times 5 out of 11 times 4 out of 10. Okay. So again, just talking about multiplying fractions, the way to get 120 is to take 6 times 5 times 4, and the way to get 1,320 is to take 12 times 11 times 10. Okay, so when we have and probability, just as a recap, there's a couple possible options. They could be independent events, meaning one is independent or does not depend on the other. This usually has to do with, depending on what we're talking about, dice or rolling die or flipping coins. Okay. The other possible that I talked about in the previous lecture is having children. Just because you've had 3 girls doesn't mean that the next one will be a boy. And then dependent events have to do with something being taken out or one event depending on the other. Okay. Let's talk about or probability. So or probability deals with non-overlapping events. So 2 events are non-overlapping if they cannot occur together. So for instance, non-overlapping events would be a coin toss. You can't get heads and tails at the same time. You will get heads or tails. Okay. So the probability of A or B is calculated by the probability of A plus the probability of B. So taking a look at this, suppose you roll a single die. What is the probability of getting a 2 or a 3? So these are non-overlapping events because you cannot get a 2 and a 3 at the same time. You can have a 2 or a 3. So you would calculate the probability of a 2 would be 1 out of 6. The probability of rolling a 3 would be 1 out of 6. So to calculate the probability of a 2 or a 3, we would have 1 over 6 plus 1 over 6. Now you can do this in your calculator. When fractions have the same denominator, you add the numerator and keep the denominator the same. So this would be 2 out of 6 or 1/3. The other way I think about this is when I see the word or there and I know that they're non-overlapping, let me do this in a different color. I would be, excuse me, happy with the event of 2 or the event of 3. So going back to calculating the probability, it's your events over your outcomes. So I would be happy with 2 events, meaning a 2 or a 3 out of 6 possible. So that's another way to get that as well. And then here's the solution again, just typed out for you. Or events, so overlapping. So with or, we can have non-overlapping or overlapping events. 2 events are overlapping if they can occur together, like the outcome of picking a queen or a club. So for instance, there are 4 queens in the deck, the queen of diamonds, hearts, spades, and clubs. And there's also 13 clubs in the deck. One of those happens to be the queen of clubs. So in this case, you can draw a queen that is a club. So this would be a type of overlapping event. Okay. So if it's overlapping, we have the probability of A or B is equal to the probability of A plus the probability of B minus probability of A and B. Okay, so this is what we're doing, is subtracting out repeated items that have been accounted for. Okay, so what is the probability that in a standard shuffle deck of cards you will draw a 5 or a spade? So this is an example of an overlapping event because you can draw the 5 of spades, which would be both of those. Okay, so in order to calculate this, we need to calculate the probability of drawing a 5 plus the probability of drawing a spade. Oh, my S's and 5s look the same. Let me do this. Spade. Minus when it talks about A and B, that's happening together. So minus the probability of drawing the 5 of spades in particular, and that would be the repeat that the previous slide was talking about. So the probability of drawing a 5, there are 4 5s in the deck. So 4 out of 52. The probability of a spade, there are 13 spades. Okay, and the probability of the 5 of spades is there's only one of those. There's only 1 5 of spades, so that would be 1 out of 52. Okay. So if we're going to set this up, these are overlapping events, so using probability of a 5, which was 4 out of 52, probability of spade, which was 13 out of 52, minus the probability of 5 and a spade, or the 5 of spades, is 1 out of 52. So you do the subtraction, so take 4 plus 13, 17 minus 1, which is 16, how to get the numerator, and then the denominator stays the same. So this probability would be 4 out of 13. Okay, so with OR events, you can have non-overlapping or overlapping events, and depending on which it is, will determine how you calculate the probability there. Okay, so the at least one rule. So suppose the probability of an event A occurring in a trial is P of A, or probability of A. If all the trials are independent, the probability that an event A occurs at least once is given below. So sometimes it's easier to calculate. So for instance, and I think the next example we'll do is tossing a coin 3 times and getting at least 1 head. Sometimes it's easier to figure out the probability of no heads or not happening and then do 1 minus that probability. So that is what this at least once rule is telling us here, that if we want to know the probability of at least one event happening, we can take 1 minus the probability of it not happening. Okay. So 3 coins again. So use the at least once rule to find the probability that at least 1 head when you toss 3 coins. So at least 1, the reason why it's easier to do the 1 minus or the complement is because at least 1 means you could get 1 heads, 2 heads, or 3 heads. It's not so bad when we're flipping a coin 3 times, but if we have like 9 or 10 trials or something higher, this is going to be a little bit easier. Okay, so rather than finding the probability or starting off directly calculating the probability of at least 1 heads, let's calculate the probability of no heads. Okay, and the probability of tossing no heads, so these events are independent, and so we would be using the multiplication that we talked about at the beginning. So probability of no head, the first time would be 1/2, the second time would be 1/2, and the probability of no heads on the third try would be 1/2 as well. Okay, so in order to calculate this, then we're taking 1 minus the probability of no heads in 3 tries, which would be 1 minus 1/2 times 1/2 times 1/2. And again, that's because those are independent events. When you're tossing a coin, the second toss doesn't depend on the first toss. Okay, sometimes superstition would lead us to think that way, or feeling would lead us to think that way, but mathematically or theoretically, that's not guaranteed to happen. Okay. And so this comes out to be 1 minus 1/8. You can put this into your calculator, but you get a final answer of 7/8 here. Okay. And again, the math is written out. The at least once rule tells us that the probability of at least 1 head in 3 tosses is equal to 1 minus the probability of no heads in 3 tosses. Okay, and so this 1/2 cubed comes from, on the previous slide I showed you, no heads on the first trial is 1/2, no heads on the second trial is 1/2, and the probability of no heads on the third trial is also 1/2. If you have any questions, please feel free to reach out to me.